Good to see you again. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering, EDRA, Ichalkalji, which is at Kolhapur district, Maharashtra. Today, we'll see the solid modeling techniques in CAD. So, most of geometric objects that we see every day are solids. That is, they are geometric objects with an interior, isn't it? The solid models are known to be complete, valid, and unambiguous objects. And solid can be very simple like a cube or very complex like turbulent blade, isn't it? So we'll see what are the applications of solid modeling. In a mechanical engineering, a solid model is used for the following applications. One is a graphics, the generating drawings, surface and solid models. And second one is for design, that is mass property calculation, interference analysis, finite element analysis, kinematic and mechanism analysis, animation, etc. So on. And manufacturing, the third application is of in manufacturing, tool path generation and verification, process planning, dimensional inspection, tolerance and surface finish and all. And it comes even up assembly as well. The application to robotics and flexible manufacturing, assembly planning, vision algorithm, kinematics and dynamics driven by a solid models. These are some applications of solid model. So we'll see now modeling considerations of solids. In order to be processed by components, solid must have some representations that can describe the geometric and characteristics completely. A good representation should address the following some issues. One is a domain. While no representation can be described all possible solids, representation should be able to represent a useful set of geometrical objects, isn't it? So an unambiguity, when you see the representation of a solid, you will know that is being represented without any doubt. An unambiguous representation is usually referred to as a complete one, right? So uniqueness, uh, that is, you can say, uh, there is only one way to represent a particular solid. If representation is unique, then it is easy to determine if two solids are identical, since one can just compare their representations. And one is accuracy. Accuracy representation is said to be accurate if no approximations is required. And if you say then validness, this means that a representation solid not create any invalid or impossible solids. More precisely, a representation will not represent an object that does not correspond to a solid. So closure is a solid will be transferred and used with other operations such as union and intersection. We'll see what is that union intersection. And the closure means that transforming a valid solid always yields a valid solid. And last, there is a compactness and efficiency. A good representation should be compact enough to save space and allow for efficient algorithms to determine the desired physical characteristics. And these issues may be contradictory to each other. For efficiency purposes, a curvilinear solid may be approximated by a polyhedron. There are many efficient and robust algorithms for handling polyhedra. However, accuracy may not be maintained in the process of approximations. If you say, for example, given two curvilinear solids that are at a tangent to each other, this tangency may disappear after conversion of the solid to be polyhedron, right? So this is what a modern modeling consideration in of solids. And next we'll see the solid modeling techniques. What are the solid modeling techniques? There are various methods of representations as the solids are. Half space method, boundary representation method, we can say that BRIP method, and constructive solid geometry, that is CSG, or you can see even CREP, and sweep representation, analytical solid modeling, primitive instancing, and spatial partitioning representation. In that, cell decomposition, spatial occupancy, enumeration, octree, encoding. Right? These are some solid modeling techniques. So now we'll see here solid modeling scheme. What exactly the solid model can be generated by the following scheme. One is we are going to see these two, the boundary representation, that is BRIP, and constructive solid geometry, that is CSG, right? And boundary representation, that BRIP uh, can be considered as an extension of the wireframe method, and the merit of the BRIP is that a solid is bounded by its surface and has its interior and exterior. Here, the boundary representation, for short, can considered an extension of the wireframe model. The merit of B is that of BRIP is that solid is bounded by its surface and has its interior and exterior. The surface of model consists of a set of well organized faces, and of you can see here there are two types of information in the BRIP, that is topological information and geometrical information. If you see, uh, that surface of the solid consists of a set of well organized faces, each of which is piece of some surfaces, uh, that is a surface path, we can say. The faces may shave vertices and edges that are curved segments. Therefore, a B-rep is an exterior of the wireframe model arrived at by adding the faces information to the layer. There are again two types of information in B-rep, that is we can say it is topological and geometrical information. The topological information provides the relationship among vertices, edges, and faces, similar to that user in the wireframe model. In addition to the connectivity, topological information also includes orientation of edges and faces as well. In the geometrical information usually includes equation of the edge and faces. The orientation of each face is important. Normally, a face is surrounded by a set of vertices. Using a right hand using handed rule, the ordering of these vertices for describing a particular face must guarantee that the normal vectors of the face is pointing to the exterior of the solid. Normally, the other order is counterclockwise. If that face is given by equation, the equation must be rewritten so that the normal vector at every point on the part of that is being used as face points to the exterior of the solid. Therefore, by inspecting normal vectors, one can immediately tell the inside and outside of the solid under BRIP. This orientation must be done for all the faces. If you see this figure, three faces and their outward pointing normal vectors, in order to describe the top surface, the vertices should be 6, 7, 2, 1, or 7, 2, 1, 6, or 2, 1, 6, 7, or 1, 6, 7, 2. In order to describe the left face, the order should be 1, 2, 3, 4, 2, 3, 4, 1, or 3, 4, 1, 2, or 4, 1, 2, 3. Unfortunately, not all surfaces can be oriented this way. If the surface of solid can be oriented this way, it is called orientable. Otherwise, it is not an, or you can say it is non-orientable, like this. So next we'll see the solid model generation using BRIP. So this is what polyhedra with face of the inner loop, and the polyhedra with a knot through the hole. This is a boundary hole. So these are some polyhedral with handles. This is some solid model generation using by BRIP. If you see advantage of BRIP, and appropriate to construct solid models of unusual shapes, relatively simple to convert a BRIP model to the wireframe model. And the disadvantage is requires more storage, yes, and not suitable for applications like toolpath generation, and it is slow manipulation. And one of their thing is the constructive solid geometry. Is one other part, the constructive solid geometry. In the constructive solid geometry, or you can say CSG, uh, another way to represent solids, it's another represent of solid modulus. A CSG solid is constructed from a few primitives. You can say that block, wedge, sphere, cylinder. This is block, cylinder, sphere, right, cone, wedge, or torus. If you see block, this can be a cube whose geometry is defined by its width, height, and depth. And the cylinder, this is right circular cylinder whose geometry is defined by its radius, isn't it? Radius and length, that h. And if you see sphere, this is defined by its radius r or diameter d. And the cone, this is a right circular cone whose geometry is defined by base radius r or diameter d and height h. And this wedge, this is a right angle wedge whose height h width w, and base depth is of d form its geometric data. And torus, its a geometry is defined by the inner radius r1 or diameter d1, we can say, and the outer radius r2, and the outer radius, that is r2, that is diameter of d2. Here these are the some primitives of CSG solid construction, from a few primitives. Then with that Boolean operations, this construction solid geometry is a construction solid geometry. It's a we have already said that it is a way of representing solids, and it would be a with primitives and Boolean operations. What exactly Boolean operation is? That we can combine two instant tainted and perhaps transformed primitives into one with union. That is, we said one with the union, or we can say here Boolean operation, that is union, that is u, intersection, that is intersection, and subtraction, that is minus. Thus CSG solid can be written as a set of equation like, so you can say here uh, we can combine two instantaneous and perhaps in transformed primitives into one with union, instruction, intersection, and subtraction operations, and these operations are called Boolean operations. Boolean operation, given two sets of a and b, you can say its union consists of all points from either a or b. Its intersection consists of all points in both sets, uh, and its difference written as a minus b, or respectively b minus a, and consists of all points in a but not b, represents in a b but not a, b but not a, sorry, b but not a. In the following, this is what Boolean operations. These are some examples we have shown here. The next one is, we can say, the data structure of the CSG representation are based on the concept of trees. And the data of the solid model is stored in its database in the tree called CSG tree. A CSG tree is defined as an inverted ordered binary tree whose leaf nodes are primitives, or you can say solids, and whose interior nodes are regularized set operations. Inverted means that the tree is upside down, its root is on the top. Ordered means that each tree node has a left and branches. A binary means that each node has two branches. If you see a figure here, if you see a figure here, it shows a CSG tree. This is show with its full detail, that is primitives, a Boolean operation, primitive with a Boolean operations, including this, you can say arrow here, right? The total number of nodes in the CSG tree of the given solid is directly to the number of the primitives that the solid is decomposed into. The number of primitives decides automatically the number of Boolean operations required to construct the solid. If the solid has n primitives, the solid have n primitives, then there are n minus 1 Boolean operations for the total of 2n minus 1, you can say. The nodes in the CSG tree, the balanced distribution of these nodes in the tree, you can say n1 plus nr, that is equal to n minus 2, where n1 and nr are the number of nodes of the left and right subtrees respectively. And if you say a perfect tree results only if the number of the primitives is even, the following relation applies to the perfect tree, that is n1 equal to nr equal to n minus 1. Yes, so this is what a CSG tree, how they have mentioned. If you see the advantage of solid modeling, it has all advantage of surface model, that is uniqueness, non-ambiguous, elastic surface profile, and this plus volumetric information, and it allows the designer to create multiple options for a design. And in 2D standard drawing, assembly drawing, and exploded views are generated from the 3D models as well, and it can easily to be exported to different finite element methods programs for analysis as well. And here, and mass and volumetric properties of an object can be easily obtained. Total mass, mass center, area and mass moment of inertia, volume and radius of gyration as well. So this is some advantages of a solid modeling. And here are the some disadvantages of the same. The more intensive computational than wireframe and the surface modeling, and it requires more powerful components that are faster with more memory and good graphics, and it's not a problem anymore. Means it's kind of a disadvantage, but it's not a problem at all. Yes, so this is what we have gone through a solid modeling. So next video we'll see another part of it. Thank you, thank you one and all.